So in this module, we will implement an LSTM autoencoder based anomaly detector in Keras. So for this demo, we will use a dataset provided by the Case Western Reserve University. We start with an ETL, which stands for Extract Transform Load process, which acquires data remotely, transforms it, and loads it to our final storage system, object store in that case. The researchers recorded different sessions of accelerometer data placed at different positions of a test apparatus with healthy and faulty bearings at sample rates between 12 and 48 kHz. All the files are in MATLAB format and different subpages are provided, containing healthy and different types of faulty data for download. So there is a relatively low amount of healthy data available. Only 4 recordings. So let's download these 4 files first. This is straightforward. After download completes, we move those files to a subfolder called CWR Healthy. Let's have a look at the contents. Okay, great. We have our 4 MATLAB files. Luckily, the scikit-learn package of Python has a function to read MATLAB files. Let's examine the objects it returns by just loading a single file. This is a Python dictionary with 2 important entries for the 2 accelerometers. Each one contains a vibration sensor data time series as a Python NumPy array. So the read folder function traverses through the folder of MATLAB files and extracts the 2 NumPy arrays. Data quality is not 100% optimal, therefore we have to filter out some crappy data where the length of the time series in both entries of the MATLAB file is not the same. We add a column to the array which indicates the file ID so that we know the source of the data, in case we need it later. Some MATLAB file doesn't contain 2 sensor readings, therefore in that case we fill the other column with zeros. We do this for every file and finally append it to a final array, which we return. So let's execute this function on the healthy dataset. So we've created a NumPy array. This is what we expect. And this array contains 3 dimensions. One is the file ID and the other 2 are the 2 time series for the 2 accelerometers. For convenience, we create a pandas data frame out of the NumPy array and write it to a CSV file. Looks nice. Note that pandas created a 4th column for us, which contains a continuous sequence number, which can become handy at some point. Note that time series are useless once you don't get them in correct order. Therefore, we can sort over the columns and ensure the correct ordering. Let's have a look at the faulty data. Many more entries are present here and picking those by hand is quite tedious. Therefore, we will automate this. We just extract URLs from the HTML file and only download those. So first we get the HTML file. Then we filter out the lines containing MAT and HTML. Then we split those lines a bit in order to extract URL to the MATLAB file. And then it looks like this. Once we have the URL, we download the file. We do this for all 3 web pages containing the different types of anomalies. And finally move everything into a folder called CWR Faulty. This takes a while, so let's go for a walk and come back later. So this is done and we've downloaded all the files. Again, we create a NumPy array containing all the data we want. And finally store it in a CSV file. This file is a bit bigger, so let's have a look. Okay, it's 1.4 GB. It makes sense to use Apache Spark for managing the files, so we create an Apache Spark data frame out of them. And at the same time, we register the data frame as a temporary view so that we can run SQL statements against it. So for example, let's check how many samples we have per file. So it's between 1/4 and 500,000. This is sufficient, but note that data is sampled between 12 and 48 kHz. So this is only a couple of seconds worth of data. So we do the same for faulty data. Since we are sorting ascending, we are sure that we have at least 2 to 3 seconds worth of data per instance. Now it's time to finish our ETL process by storing both data frames as Parquet files into object store. Parquet is a very cool compressed column store format, and from the 1.4 GB I think we will end up only with 100 or 200 megabytes. In order to get the credentials for the object store, the most convenient and easy way is to just upload a dummy file. I've done this already. And then insert a Spark session data frame into the notebook. Once the credentials are inserted, we can use the object store as an ordinary file system or like HDFS within Apache Spark in the notebook. So let's store both data frames as Parquet files in object store. Note that I'm temporarily changing the file name since I've done this already and I haven't deleted those. So we have now written more than 33 million of samples. Let me just double check where the data has been stored to. To do so, we enter the IBM Cloud Console and click on the appropriate object store service. So we can see that the Parquet file has been split into multiple subfiles. We can prevent this by calling the repartition function on the data frame. But let's skip this for now. It's anyway a good practice to repartition the data according to the number of workers we have in the Spark service. Now it's time for the actual implementation. Note that ETL often takes between 80 and 95% of your time, so now we deserve to have some fun. Again, we use the same credentials in order to read files from the object store. We could have used the local file system which Data Science Experience provides as well, especially since it provides a staging area of nearly 100 terabytes for us for free. But this file system is volatile, so we are better off using object store, which is permanent. So let's treat the two data frames and register them as temporary query tables in order to be able to execute SQL statements against them using Apache Spark. We need a couple of imports. Then we define a class called lossHistory. This is a so-called callback handler, which is called by Keras every now and then to record a trajectory of losses during training. It's not every now and then, actually it's called on the beginning of every training epoch. Now we define that we are working on count-based windows of 100 samples. This means we are using 100 past samples to predict 100 future samples. In a sense, this is exactly what time series forecasting does. The dimension is 2, since we have 2 accelerometer sensor readings per instance. Now we create an instance of our callback handler and start with a sequential model. We add an LSTM layer which has 50 neurons and expects input as 100 by 2 to D array. The output layer is of dimension 2 again, since we are going back to our input shape, which are the 2 dimensions of the 2 accelerometer readings. Now we compile the model and define 2 important parameters. First we tell Keras to compute loss with the mean average error function, and then we use the Adam gradient descent optimizer. We define a train function which calls fit on a model with the following important parameters. We train for 20 epochs, that means we are showing the data 20 times to the model. Batch size 72 means that every 72 samples the weight parameters are updated. Please note also that we are passing the data twice, as input and as output. This is how an autoencoder works. So in order to train the model, we want to use the different data instances, or in other words, data which comes from the MATLAB files. To be 100% sure that we are not messing up with ordering, we sort the data based on the sequence column. Then we filter by file ID. This ID we've directly obtained from the file name of the MATLAB file. Finally, we return only the 2 columns containing accelerometer data. We unwrap the data frame to obtain the RDD and map on it in order to unwrap data from the row objects. Collect pulls data back to the driver as a Python array, and this we wrap as a NumPy array. Since we are working with count-based tumbling windows of size 100, we need to make sure that we fit to those stride. Therefore, we just remove all data which doesn't fit into multiples of 100. So trim now contains the remainder, which we simply cut away using NumPy slicing syntax. Then we turn this 2D array into a 3D one by taking the tumbling window size into account. This way the array perfectly matches the shape of the input of our neural network. Finally, we return the array. Since we have this cool and handy function in place, we now can iterate over an array of file IDs. We can obtain those from the data frame as well by selecting the distinct of that field, since we have stored the file ID to each sample as well. Note that again we need to unwrap and collect the data back to the Spark driver. Since training a neural network takes a bunch of time, we measure it. Let's start a stopwatch here. This body of this loop will be executed for each file ID of the healthy dataset. And for each file ID, we get a recording which we can directly feed into the neural network for training. After the job has finished, we see that it ran on 3 recordings and took roughly 11 minutes for all them and 4 minutes per recording. Now let's plot the trajectory of such a training in order to see how it converges. It actually converges really fast, which is very nice, especially since our neural network is fairly simple. Later we see a more complex neural network with more complex data. The 2 spikes which we are seeing here are mostly occurring because of the switch between the different recordings of the training dataset. Now let's examine a faulty recording and see how the neural network behaves. We expect a sudden increase in loss, especially at the beginning of training. We append the obtained losses from the callback class to the previous losses when training on the healthy dataset and plot it. And we see a clear spike in loss once the neural network sees faulty data for the first time. Note that the loss decreases over time, so there are a couple of additional steps to turn this into an out-of-the-box anomaly detector. So let's examine this in the next video. So we have done our homework for now, so let's see how we can turn this into a solution exemplified by a cognitive IoT real-time anomaly detection system.